Hello and welcome back. Thank you for joining me again. In this lesson, we'll explore horizontal asymptotes in rational functions. Recall that a horizontal line consists of infinitely many points that all have the same y-coordinate. For example, every point on the horizontal line y equals 3 has a y-coordinate of 3, while the x-coordinate can take any value. A horizontal asymptote is also a horizontal line. It represents the value that a rational function approaches as x becomes extremely large in either positive or negative direction. But how are the horizontal asymptotes formed in rational functions? Well, as we move further and further to the right or to the left of the graph, the y values may approach a constant value. In other words, as x approaches positive or negative infinity, the y values continue to change, but the changes become extremely small. For example, if the y value approaches 3 as x becomes very large, then the graph has a horizontal asymptote of y equals 3. Unlike vertical asymptotes, horizontal asymptotes may be crossed by the graph. A horizontal asymptote describes the end behavior of the function, and it doesn't necessarily restrict the domain of the graph from touching or crossing the line. Horizontal asymptotes become easier to understand when we examine some algebraic or we study them through algebraic examples. So in the first case here, we're looking at rational functions where the degree of the numerator equals the degree of the denominator. So let's take a look at our example 1, where we have a linear over a linear function. Now, to discover the horizontal asymptotes, we are going to send x to infinity, because horizontal asymptotes are formed as x, or are describe the end behaviors of a function, and then we'll have to determine the y values. So in order to do this, then I'm going to rewrite my function here and make x equal to infinity. So 2 times infinity minus 6 over infinity minus 6. Let's see what we can get here. 2 times infinity, infinity minus 6, that's infinity. Infinity minus 6, that's infinity again. And this is when we run into a problem. So if we were to evaluate the value of y, we get infinity over infinity, and we know this is undefined. We studied this in the first part at the beginning of this lesson. So now we're thinking, how can we estimate what happens to the y values as x approaches infinity? Because it's not that the function is not defined. The y values aren't defined as x approaches infinity. So the graph should exist. Well, in order to answer or to solve this problem, we have to think backwards. So this is undefined because we have infinity in both numerator and denominator. That's the cause of the fact that we cannot evaluate it. Now we have to think what brought infinity to both numerator and denominator. Well, the presence of x, the variable x did. So now we're thinking, is there a way that we can simplify x before we substitute x by infinity? So we're going to give that a try. And for this, we'll have to factor the variable x from both numerator and denominator. And before we do this, I'll show you a very quick example. Remember that whenever you are factoring, let's say, number 2 from this polynomial expression, then the way that you figure out what's left of 6 is by dividing by 2. We can very intuitively and very quickly find this, but the mathematical operation behind it is you take negative 6 divided by 2. So we're going to follow the same strategy here as we factor out x. So y will be equal to x. So if you take x out of 2x, 2 is left in. And if you take x out of negative 6, then we'll have to take negative 6 and divide it by whichever factor we took out. So negative 6 over x. Now, in the denominator, we're doing the same thing. You take x out of x, you are left with just 1. And then the negative 4 will become 4 over x. Negative 4 over x. So let's simplify x. And the simplified form of our function will be 2 minus 6 over x, 1 minus 4 over x. Now, let's substitute x by infinity and see what happens. Since it is in more simplified form, we're hoping that a miracle happens here. Substitute x by infinity. Now you can see that 6 over infinity is 0, 4 over infinity is also equal to 0. So what that means is that here we're going to have 2 minus a 0 plus. And in the denominator, we have 1 minus a 0 plus. So in other words, here we're going to have 2 minus 0 plus a little bit less than 2 divided by a little bit less than 1, or approximately, because remember we're estimating here, we're going to have just 2. So we're going to say that the values of the function as x approaches infinity will approach a positive 2. Therefore, we're going to say that the horizontal asymptote will be at y equals 2. Now, just like we evaluated or estimated the value of y here as x approaches infinity, we can do the same thing when x approaches negative infinity. And I wanted to very quickly kind of verify this one in here. So if we have 6 over negative infinity, 4 over negative infinity, here we're going to have a plus 0 instead, because this is going to be a 0 minus. So minus 0 minus is a 0 plus. And that will end up being 2 plus over 1 plus. It's still going to be equal to 2. So y equals 2 is the horizontal asymptote. Now, next we're going to look at example number 2. In example number 2, we have x squared plus 2x plus 1 over 5x squared minus 3x minus 2. I learned from the previous example, if I bring infinity in, then I will end up with infinity with some other forms of infinity here. So what I'm going to do is try to get rid of the variables that bring infinity in. And I don't mean just x to the power 1. I have to take out x to the highest power. So this would be y equals x squared, 1 plus, again in the same way, 2x divided by x squared will be 2 over x. And then 1 divided by x squared is going to be 1 over x squared. And down here we have x squared again. And then 5 minus 3 over x minus 2 over x squared. So x squared and x squared will simplify. And our function is turned into this very good looking function, by the way. And 5 minus 3 over x minus 2 over x squared. So let's substitute x by infinity and see what happens. So 1 plus 2 over infinity plus 1 over infinity squared, 5 minus 3 over infinity minus 2 over infinity squared. So notice how in this case now we're going to have 2 over infinity is a 0, 3 over infinity is a 0, 1 over infinity squared is a 0, 2 over infinity squared is a 0. So they're all zeros. You're going to say, well, 0 plus and 0 minus, they're all zeros. But let's say that we want to be very precise in here, or as precise as we can. So 1 plus 0 plus plus 0 plus over 5 minus 0 plus minus 0 plus. So that will change this to become a 1 plus. And here we're going to have a little bit less than 5. So in other words, we're going to have 1 over 5, if you were to compare it, 1 over 5 is going to be 0.2. But if you divide 1 plus by 5 minus, it's going to be a little bit more than 0.2. And I'm going to keep this number in here. And this is going to be approximately 1 over 5. The function will not be exactly 1 over 5, but close to it. And in this case, then, we're going to say that the function has a horizontal asymptote of 1 over 5. Now, what happens when the function has a horizontal asymptote at 1 over 5 means that if the horizontal asymptote, let's say, is here at y equals 1 over 5, then you see that the graph of the function as x approached positive infinity was 0.2 or 1 over 5 plus. So that means that the graph of the function will be above the horizontal asymptote. Okay? Now, let's bring this to the other side. And I also want us to take a look at negative infinity, what happens to the graph of this function as x approaches negative infinity. Let's do this. Now, we don't have to do all the steps in here. We can just start from here and estimate the value of the function. So that's going to be 1 plus 2 over negative infinity plus 1 over negative infinity squared, and then 5 minus 3 over negative infinity, and then minus 2 over negative infinity squared. So in this case, we're going to have 1 plus a 0 minus plus a 0 plus, and then down here we have 5 plus 0 plus, and then minus 0 plus. So how do we determine this? Minus and minus will make a plus, so that's a 0 plus. And this one here is a minus. This will turn into a 0 plus, so minus 0 plus. Now that's another operation that is very hard to estimate. So we can't tell right away whether the function is going to approach this horizontal asymptote from above, like we were able and certain in here, or from below. So in cases like this, what you want to do when you graph the function is give x a very large negative number to see if you get a number bigger than 1 over 5 or less than 1 over 5. So slightly, obviously. But as you can see, an estimated value of it is still 1 over 5. So as x approaches negative infinity, y will approach 1 over 5, making the horizontal asymptote again at y equals 1 divided by 5. But again, if you want to be more specific and try to understand whether the function will be above or below the horizontal asymptote and in the left hand, then you would want to give a specific value, because sometimes it is difficult to estimate these expressions. Now, there is something else that I want to bring your attention to. Now, we found out here that in the first example that y equals 2, and this was our function right here. And for the next function, we found out that the horizontal asymptote is at y equals 1 over 5. I've made the classic mistake in here that I intended to show as something that we should not do. Always write the asymptotes using their equations. Okay, so I wanted to try to recognize some patterns in here. So y equals 2, where does this come from? If you were to compare the leading coefficients here, 2 over 1, that's 2. If you were to compare the leading coefficients here, 1 over 5, that's 1 over 5. So we can use this as a shortcut to determine the horizontal asymptotes. We're not going to do this all the time unless you are specifically asked to analyze it. So you are simply going to take a look at the coefficients, and this is when we draw the conclusions. So how is the equation of the horizontal asymptote related to leading coefficients? It seems that it is the ratio of the leading coefficients. And that's how we are determining the horizontal asymptotes from now on. Now, what happens if the degree of the numerator is lower than the degree of the denominator? When that happens, then what we are going to do here, as you can see, we have degree 1, degree 2, is take out x squared from both numerator and denominator. And in this case, we're going to end up here with 2 over x plus 1 over x squared. And down here we have x squared and then 1 minus 9 over x squared. Simplify x squared. So here's f of x equals 2 over x plus 1 over x squared over 1 minus 9 over x squared. So if we let x approach infinity, then we'll have 2 over infinity plus 1 over infinity squared, 1 minus 9 over infinity squared. So notice how all these numbers in here will turn into real numbers, estimated values, right, of 0. So 0 plus 0, that would be equal to 0. And 1 minus 0, that would be 1, which tells us that 0 over 1 is 0. So therefore, we're going to say that f of x will approach 0 as x approaches infinity. That means that the horizontal asymptote will be at y equals 0. We'll do the same thing with the next function, 5x minus 20 over x squared minus 5x plus 6. And you can try to do this on your own. It's not difficult. I will continue here. So we have g of x equals, again, I'm going to take out the greatest power, so which is x squared, from both numerator and denominator. So x squared and then 5 over x minus 20 over x squared. Now x squared, 1 minus 5 over x plus 6 over x squared. Simplify, and now we get 5 over x minus 20 over x squared over 1 minus 5 over x plus 6 over x squared. So here we go again. We're going to have 5 over infinity minus 20 over infinity squared over 1 minus 5 over infinity plus 6 over infinity squared. So here we go again. We have 0 minus 0, that's a 0. And 1 minus 0 plus some other 0, that would be 1. And that means that the answer is 0, so there will be a horizontal asymptote at y equals 0. Now let's take a look at both examples. So in both examples, where we had linear over quadratic, notice that the horizontal asymptote ended up being the same. So we can think, would that be the case all the time, and why is that? Now, whenever the numerator has a degree lower than denominators, the horizontal asymptote will always be at y equals 0. And the reason why is because algebraically we saw it that when x approaches infinity, now these terms in the numerator all turned into 0. But there is another way of looking at it that I would like to explain it. If we follow the same strategy as we did in the previous example, because we are making too many rules for the horizontal asymptote, the rule that applies to this case and to this case, I prefer that we learn one rule that works for all. So would we be able to actually use the same strategy as we did in the previous examples when degrees were the same to determine the asymptote? Well, if we were to do that in our first function in here, it means that since we don't have an x squared term, x squared is the degree of the denominator and it's higher than numerators, then you can rewrite this as 0x squared plus 2x plus 1 over x squared minus 9. Now you can see that the leading coefficients of variables of the same power are 0 over 1. So the leading coefficient 0 over 1 is 0, therefore horizontal asymptote will be at y equals 0. So that is a more solid way of remembering one rule for horizontal asymptotes and applying it everywhere. So you can either memorize that when degree of numerator is less than denominators, horizontal asymptote is at y equals 0, but this is a nice way to understanding why and how that happens. Excuse me. So how do we find the horizontal asymptotes? So to find the horizontal asymptotes, we always start off with comparing the degree of the numerator with denominators. And if the degrees are the same, that's our step number 2, then we're going to say y equals the ratio of the leading coefficients. If the degrees are different, we have to make them the same by filling it with terms. Excuse me. And then determine the horizontal asymptote again as the ratio of the leading coefficients. Let's take a look at some examples. In the first example, we have 5x squared plus 1 over 3 minus 2x squared. Power 2, that's the highest power. Therefore, y equals negative 5 over 2 is the horizontal asymptote. Power 2, the highest power is the same. Coefficients are 2 and 1. Y equals 2. Here we get power 2, power 1. If I had a power of 2 here, that would have to be 0x squared. So ratio of leading coefficient will have to be 0 over 2, so y equals 0. Here we have power of 2. This is a constant. If I had to have an x to the power of 2, I would have to give a coefficient of 0. So y equals 0 over 1 or y equals 0. Next, we have power 2. Power 2, straightforward, leading coefficient ratio is 3 over 4. That will be the horizontal asymptote. And let's take a look at this example. We have same powers to both numerator and denominator, same highest powers. So we're going to look at their leading coefficients, and that will make the horizontal asymptote at negative 7 over 2. Now, to determine the horizontal asymptotes, we use another strategy that we call polynomial division. And for this, I am going to actually use the examples that we have studied already so that we can compare the answers. Now, normally, the horizontal asymptotes can be seen as the quotient that results from the division of the numerator with denominator. Try it. And you will see that in every division that you would perform in here, you would get a quotient equal to exactly the horizontal asymptote. So we're going to say that 2x squared goes into negative 7x squared, negative 7 over 2 times. Negative 7 over 2 times negative 2 is 7x to the power of 2. And then subtract 0 plus 3. It doesn't go anymore. This is where you stop the division. So whatever you get in the quotient, that will be actually your horizontal asymptote. That's just another way of looking at horizontal asymptotes, which will be very helpful, especially when we look into the next type of asymptotes, the oblique asymptotes. That is going to be in the coming lessons. But until then, thank you for learning with me, and bye for now.